Good morning students. In this video, I will be discussing on what is pulse code modulator. Okay. To convert any analog signal to a digital data, normally we use two techniques. One is pulse code modulator, the other one is the delta modulator. However, in this video, I will be discussing on only pulse code modulator as it is the most useful technique to convert any analog signal into a digital data. So normally in order to convert an analog signal into a digital data using pulse code modulator, we are following three steps. One is known as sampling, the other one is quantization, and lastly binary encoding. So among these three steps, quantization is very important. Okay. So this is the diagram. So this is what your analog signal that is given as input to the pulse code modulator encoder, where there are three steps involved. One is known as sampling, a simple technique where we are going to convert the signal into analog values. The second step is the quantization technique, very important technique. And lastly, we have an encoding technique where the analog signal will be converted into digital data. So the first step, as I told, analog signal is first sampled every t seconds. Okay, and you should also know that fs is nothing but 1 by ts. That is, sampling frequency is nothing but the reciprocal of the sampling rate. Okay. So the process is referred to as pulse amplitude modulator. So the process that we are using here in order to sample our data, we call it as pulse code amplitude modulator, and the outcome what we get in this method is known as analog values. So there are three types of sampling techniques. One is known as ideal sampling, the other one is natural sampling, and what we call it as flat toss sampling. So ideal sampling means every t seconds, means every fraction of seconds they are going to what we call that sample the analog signal. Okay. So natural sampling is almost same, where the time when compared to ideal sampling is somewhat less to sample the analog signal. And flat top sampling is one more technique where you can see the signal is in the flat top shape. So there are a number of techniques where we are going to convert an analog signal into an analog what you call that values using sampling techniques. So these are just sample three techniques I have shown. Okay. So coming to next very important step is quantization method or a quantization technique. So here we need to assume the original analog signal has been instantaneously amplitude between V minimum and V max. So we need to assume some values, the highest voltage and the lowest voltage. Okay. Then we need to divide the range into L zones. The complete signal range should be divided into L zones. Each we call it as delta, height we call it as delta. So how to calculate that height delta, which is nothing but delta is equals to V max minus V minimum divided by L. So third step is we assign quantized values of 0 to L minus 1 it was to the midpoints of each zone. Don't worry, I will show in the next slide how to assign these quantized values from 0 to L minus 1. So you need to assign to midpoint of each zone. So here we got the zones. For every midpoint of that zone, we need to assign the quantized values that are ranging from 0 to L minus 1. Lastly, we approximate the value of the sample value to the quantized value. So in order to understand all these four steps, so we need one what you call that example to show how exactly these four steps will work, that I will be showing in the next slide. Okay. So as a simple example, let us assume, as I told now, here we need to assume the amplitude that is ranging from V minimum to V max. So let us assume that a sampled signal is from minus 20 to plus 20. So you can assume any values. So here you can see that this is what the values are assigned, minus 20 to plus 20 means within that range only the signal has to be sampled. So we decide to have the 8 levels. So here L is nothing but 8. So these two values we need to assume. minimum value and the maximum value of the amplitudes as well as levels we need to assume. And then we can calculate what is known as delta, Vmax minus Vmin divided by L. Here Vmax is nothing but minus 20 minus of plus 20. So you will get 40 divided by L is nothing but 8. You will get delta as 5. So using these values, now we will find the sampled values from the quantized values. So which is our first step? We assume that the original analog signal has been instantaneously amplitude between V minimum and V max. So here we are going to amplitude this analog signal. This is what my analog signal. So this has been amplitude between V max and V minimum, means minus 22 plus 20. It is sampled with some values. So it may be using sampling technique, which is my next step. So these are the values we got: minus 6.1, 7.5, 16.2, 19.7, 11.0. So this, using sampling technique, first method, we have sampled the analog signal. So just note down all these values. Okay. The second step is we need to divide the range into L zones, each of delta height, where delta is nothing but Vmax minus V minimum divided by L. So how many zones we have? We assumed 8 zones. So totally there are 8 zones. So these are the zones: 0, 1, 2, 3, 4, 5, 6, 7 and 8. And they told 0 to 4 here, 0 to 4 here. So totally 8 zones are there. And he told that we assign quantized values of 0 to L minus 1 to the midpoint of each zone. So what is my L here? Okay, 8. So 0 to L minus 1, 8 minus 1 is 7. So 0 to 7 we need to assign these quantized values to the midpoint of each zone. So here the midpoint is where? Here. So midpoint of this zone I am assigning 0, and for this zone I am assigning 1, 2, 3, 4, 5, 6, 7. So in this way we need to assign the quantized values to the midpoint of each and every zone. Okay. And then we need to calculate the sampled values. So these three things we have done. This is what our first step, where we need to sample the data. The second step is we need to take the 8 zones. And the third step is we need to assign the quantized values to the midpoint of each zone, 0 to 7. Now let us calculate the quantized values. So the first step is you need to find the normalized pulse code amplitude modulator values. So how to find it? This can be calculated with the normalized amplitude values divided by delta. What is our delta? It is 5. So here the normalized PAM values we have designed, normalized amplitude values is this one, minus 6.1 divided by delta, which is nothing but 5. So just divide it, you will get minus 1.22. Similarly 7.5 divided by delta 5, you will get 1.50. So 16.2 divided by 5, you will get 3.24. Like that you need to divide the each value by delta, where you will get the normalized PAM values. Once you get the normalized PAM values, you need to find the normalized quantized values, which is nothing but the error that is occurred between the normalized quantized values is nothing but you need to take the midpoint of the normalized PAM values. For example, minus 1.22. Okay, so the midpoint is from 1.2 to 1 to 2, so which is nothing but 1.50. Similarly for 1.50, the midpoint is 1.5 only. So 3.24, the value lies between 3 and 4, the midpoint is 3.50. Similarly 3.9, it is 3.50 because the value lies between 3 and 4. Similarly 2.20, the value lies between 2 and 3, so the midpoint is 2.50. Similarly for 1.10, the value lies between 1 and 2, so we can assign it as 1.50. And for 2.26, it is 2.5. And 1.88, the value lies between 1 and 2, so it is 1.50. And lastly 1.20, the value lies between 1 and 2, it is 1.50. So in this way, you need to find the normalized quantized values. Once it is done, then you need to find the normalized error, because these are the exact normalized PAM values what we got, and these are just midpoints we have taken. So we need to find the difference between normalized quantized values minus normalized PAM values. So minus 1.50 minus of minus 1.22, you will get minus 0.38. Similarly to 1.50 minus 1.50, 0, and 3.50 minus 3.24, it is 0.26. Like that you calculate the normalized error for each and every value. Once it is done, then you need to assign the quantized code for each and every normalized error. So how to find it? Just you see the quantized code for this normalized for this normalized quantized value. For example, minus 1.50, it lies between the zone 1 and 2, means somewhere here. Okay. So what is the quantized value for that? 2. So I am assigning 2 here. Similarly, 1.50, it lies between the zone 1 and 2. So somewhere here, the midpoint is this one, it is 5. And 3.50, the midpoint between 3 and 4. So somewhere here, it is 6. 3.50, sorry, here, it is 7. Similarly, 3.50, it lies between 3 and 4. Here again it comes 7. So like that, you assign for all the values. You assign the quantized codes. Once it is done, then very important is you need to convert this quantized code into words, encoded words, final value. So 2 is represented with 0, 1, 0. But the question is here, why we have taken 3 bits. So how many bits we need to convert this quantized code into digital data? It purely depends upon the L. So what is our L here? 8. So you need to calculate log L to the base A, log L to the base 2. So what is our L? 8. So you can just do log 8 to the base 2. Then you will get here 3. So that's what we are using, 3 bits to represent these quantized values. So 0, 1, 0 is nothing but 2, and 5 is nothing but 1, 0, 1, 7 is nothing but 1, 1, 1. Similarly, you can do for all the values. Once we got this encoded words, just you pass this to the last step, that is nothing but decoder. So we have converted our analog signal into digital data. If you want to convert this back from digital data to analog signal, then we have what is known as pulse code modulator decoder. So just you pass that digital data what we got here, okay, 0, 1, 0, all those, to this pulse code decoder. Then there is a make and connect samples, which will convert this digital data into what you call that sampled analog signal, which is passed to a low pass filter that will convert back exactly into the previous analog signal what we had. Okay. So in this way, this pulse code modulator is very helpful in converting our analog signal into digital data and back digital data into analog signal. Okay. Hope so enjoyed the video. Thanks for watching and subscribe my YouTube channel for more videos. Bye.